Alright, so in Physics 1, we normally start with a review of unit systems and fundamental units and unit conversion. So that's what we're going to do here. So there are two systems of units we usually see. One is called the International System of Units, or SI units. Okay. So this system is the most widely used system all over the world. But in this country, another widely used system, or even more widely used system, is the United States Customary Units, or USCS. Okay, so this, or like a lot of people call these two units metric and British. Okay, so but when we solve a problem, okay, in physics, we're going to convert everything into one system of units. And then the system of units that's used in physics is the SI units. Okay, so I know that more people are more familiar with metric, more familiar with British units in this country. But when we do math in physics, we use SI units. So make sure always watch the units in the problem. We are going to see both in this class. Okay, but when you solve a problem, when you do math with numbers, okay, in a problem, you're going to make sure you use SI units. So you're going to convert everything to SI units, okay? And that is a very common mistake people make. So you definitely do need to pay attention to all the units, okay? So there are three fundamental quantities and units in physics, okay? And then I'm sure that everyone's familiar with these three things. They're length, mass, and time, okay? So all other quantities and units we're gonna see in physics, they're pretty much derived units from these three units, okay? And sometimes we may give them a name, okay? Sometimes we don't, okay? So we're gonna see a lot of units in this class, but all of them are derived, just a combination of these three fundamental quantities and units, okay? Now let's take a quick look at these three quantities and units. I'm sure that everyone is familiar with these three guys. Okay, length. Length is a measure of space in any direction. Okay, so but in this universe, there are three dimensions. Okay, space dimensions. We call them length, width, and height, but they're essentially all lengths, right? We just give them different names in different directions. Okay, and the SI unit of length is the meter. So if you see you solve a problem, okay, we're going to do a lot of problem solving in this class. You see a length, you want to use the length, plug it into an equation, make sure you convert the length to meters before you do that. Okay, everything must be in SI units, so convert all the lengths to meters. Okay, then you can plug them into an equation and find things you need. Now the second quantity is the mass. Okay, mass is the amount of matter an object contains. Okay, so it's also a measure of its resistance to any change in its state of motion. Okay, so it's also related to what we're going to discuss later, inertia of an object. Okay, we're going to discuss that in detail when we study Newton's laws. So mass is an intrinsic property of an object. So that's why it doesn't change. Okay, it never changes. Okay, in normal conditions. All right. So and then the SI unit of mass is the kilogram. Okay. So again, when you see grams or things like that in a problem of an object, you're going to convert them to SI unit. You can convert them to kilograms. Okay, before you use the mass to calculate something else. So because the mass is as I said, mass is a property of an object, so it doesn't change. It's actually different from weight. A lot of people, they think these two things are the same thing because mass and weight, they're connected, especially on the Earth. Okay, most of you may already know that the weight, it's just the gravity of the Earth on us, okay, or any object on the Earth, okay. It is proportional to the mass, right? Most of you may have already may already know this equation, the weight or gravity of anything, it's mass of this object times 9.8, right? We're also going to discuss that later. And then this 9.8 is a constant, right? So the mass, the weight of anything is always proportional to this mass of an object on the Earth. So that's why a lot of people think they're the same thing. But technically, strictly speaking, they are different. They're connected, but they are totally different things. Okay? A very classical example to distinguish mass and weight is this, right? If you go to a different planet, or say you go to the moon, okay, and then the weight, your weight is gonna be smaller, okay, because the gravity on the moon is definitely weaker. It's almost 1/6 of the gravity on the Earth, okay. So if you go to the moon, you definitely feel lighter, okay. Your weight is gonna change. Your weight is going to become smaller because the force from the moon on you is going to be smaller, okay? But the mass, the number of atoms, the matter in your body contains, doesn't change. So you will still have the same mass. The weight changes because weight is the force, is the gravitational force from the Earth or the moon on you. But the mass is your own property, doesn't change, okay? Now, the last fundamental quantity is the time. Okay, everyone is familiar with this concept. Right? We use this concept every day. And then the SI unit of time is the second. So again, whenever you see your time in a problem, okay, it may be in days, hours, minutes. Always convert them to seconds before you use them in an equation to find things you need. Okay, so these are the three fundamental quantities and units in physics. And then sometimes when we deal with things in real life, okay, we may have like very small numbers and very large numbers, okay. So we use these prefixes to help us to write these units, okay. We put prefixes in front of a SI unit, okay, to help us write like very large or very small number without a lot of zeros, okay. So take a look at these common metric prefixes on slide 7, okay. So these are the very common prefixes, like mega, it's a million, right. So the symbol we use is the big M, and kilo is 1,000, okay. So the symbol we use is K, and also centi and milli and micro, okay. So when you see these prefixes, okay, in front of the SI unit, you also need to convert this combination to the SI unit before you use this number to plug it into an equation to find things you need, okay? And then how do you convert these prefixes, okay, the combination of the prefix with the SI unit to an SI unit, okay? So the rule is actually very easy. So first of all, you need to know what this prefix represents, okay? And then all you need to do is just replace this symbol, okay, with the number it represents. Then you get rid of the prefix. You only have the SI units, right? So for example, let's take a look at this question on slide 8, okay? So if I want to convert 5 micrometers to meters, right? So how do I convert? So again, if I see 5 micrometers in a problem, okay, physics problem, I need to convert it to meters before I use it to calculate something else, right? So how do I convert 5 micrometers to meters? Well, the rule is this. First of all, you need to know what micro means, right? What this mu, this Greek symbol mu means. So take a look at the common metric fixes in the previous slide. Micro, the symbol mu means 10 to the negative 6. So it means very, very small, right? So this is what we know. I know this prefix represents 10 to the negative 6. Now, if I want to convert 5 micrometers to meters, so all I need to do is just replace this prefix, okay, with the number it represents. Then you're done. You get rid of this prefix, okay? So I hope, so in this case, you would just replace that with 10 to the negative 6, meters, right? So this is just going to give you 5 times 10 to the negative 6 meters, right? And then because there's a negative sign, so you don't erase this negative sign, okay? If you make it positive, it becomes a huge number, okay? Which is not what this means, all right? So that's how we work with prefixes. And then, as I said, we're going to see, well, even in real life, we see metric and British, like all the time, right? But if I want to use, do some calculations using numbers I got, okay? I need to make sure everything is in one unit system. I cannot have like 2 of them, okay? It's like speaking 2 languages at the same time. You're going to confuse people, okay? People are not going to get what you're saying. You have to use the same language. So in physics, we use metric, we use SI units, right? So that means sometimes you need to convert units, right? You're going to convert British units to SI units. So that's what we want to review next, right? Unit conversion, okay? So yeah, I believe most of you have seen this before. The rule is this, right? First of all, you need to know the conversion factor between these 2 units, okay? For example, let's take a look at slide 10. If I want to convert miles to meters, right? So I need to know the conversion factor between them. So 1 mile equals 1609.34 meters. And once you have this conversion, you can convert meters to miles or miles to meters. Okay? So what do you do with this? For example, if you want to convert 1850 meters to miles, right? You can write down the number and the units you're given, right? Say I want to convert SI units to British. I will write down this guy, right? And then write a fraction and put these 2 numbers and units in right places so I can do algebra with the numbers and units, right? And then you see that you have 2 numbers, so you have 2 spaces. You're just going to put them in the right place, okay? And then which one goes to the top, which one goes to the bottom? You just take a look at all these units you have, right? I have meters here, I have miles and meters here, but at the end I want to get miles, right? So which one is going to go to the top, which one is going to go to the bottom? Well, then you want to cancel meters, right? So I would have to put this number with meters at the bottom, okay? And then 1 mile goes to the top, becomes the numerator. So if you only take a look at these 3 units, right? Meters and meters cancel, you will only have miles at the end. Right? So that is the unit you want at the end, okay? So that's how I figure out which one goes to the top, which one goes to the bottom, okay? And then you can go ahead, do algebra with these numbers you get, okay? 1850 multiplied by 1 and divided by this number, right? So that's going to give you 1.15, okay? And then you can also, as I said, if you have the conversion factor between these 2 units, you can go either way. You can go from miles to meters or meters to miles. So say if I want to convert 1850 miles to meters, okay, how do I do that? I'm going to still write this number and the units I'm given, write a fraction, now put them in the right places. In this case, I want to get meters at the end. I want to cancel miles. So I would have to put 1 mile down here. Okay? And then 1609.34 meters, it's going to go to the top, become the numerator. So take a look at these 3 units we got. So miles and miles, they cancel. Right? So I will only have 1 unit left at the top. So meters, that's the unit I want at the end. Now go ahead and multiply these numbers and do the algebra with these numbers, right? It's going to be this number multiplied by this number divided by 1. So at the end you should get 2.98 times 10 to the 6th. Okay? So that's the unit conversion, right? So again, first of all, you need to know the conversion factor between these two units you want to convert. And you don't need to memorize these conversion factors, okay? Physics is not about memorizing this stuff, okay? It's not about memorizing equations, okay? Memorizing facts, okay? It's about the math. It's about understanding the laws and applying these laws in a real life problem, okay? That's what we're learning in physics, okay? It's not about memorizing stuff, okay? So some people, they learn to do it in this way. They will draw like this, and then put 1850, but that's the same idea, right? Right? I know that a lot of people learn to do it this way, right? So basically, you still just cancel these meters and meters. You have miles left, and then you do the algebra with these numbers, right? It's the same idea, okay? Right? There's no difference. So now let's do practice, okay? Take a look at the question on slide 11. If I want you to convert 45 seconds to hours, okay? So how do you do that, okay? So again, I will need to know the conversion between hours and seconds. So how many seconds in 1 hour? Okay, I believe that's something everyone knows, okay? If you don't know that, you shouldn't be in college. So 1 hour equals 60 minutes, and each minute equals 60 seconds, right? So at the end you will get 3,600 seconds, okay? So once you have this conversion, you should be able to go from seconds to hours or hours to seconds, okay? Say in this question, I want to convert 45 seconds to hours, okay? So what is the answer, okay? So I usually, if I have students in this classroom, I usually have them do iClicker questions, but now I can't do that online. So, but I still want you to, after I explain this problem, okay, pause the video, do the math, and then you can compare your answer with mine, okay? You learn better if you do the work with me instead of just watching me doing everything, okay? All right, so let's see, 45 seconds, if I want to convert it to hours, write this fraction, now put these two numbers in the right places. The 3,600 seconds must be the numerator, and 1 hour must be the denominator, so that I can cancel the seconds. And then once I cancel them, you see that I only have hours left at the end. So that is the unit I want at the end. Okay, now I can do algebra, right? It's going to be 45 times 1 divided by this. So the final answer is this, right? So that's how we convert units, and it's very important in physics because you may get different units in the real problem, okay? Now you can also use this method to work with prefixes, okay? If you want to convert units with prefixes, okay? So take a look at the next question. If I want to convert 3 grams to kilograms, so kilograms is the SI unit, right? So if I see something with like 3 grams in a problem, I want to use that number to calculate something else. I should convert that to kilograms. So again, you can just use the technique we used for this unit conversion. You can think of grams and kilograms as just 2 different units, okay? So you can go use the conversion between them. You can go from grams to kilograms and kilograms to grams, okay? So in this case, we know that kilo is a prefix, right? 1 kilogram is equal to 1,000 grams. That's what kilo means, okay? Now if you have this, you treat kilograms and grams as 2 different units, you can use this fraction to convert grams to kilograms or kilograms to grams. All right? So again, now you can pause the video and do the math and see if we get the same answer. Now 3 grams, okay, write it down, and then now I'm going to write a fraction, put these two guys in the right places. I want to cancel grams. I would put 1,000 grams at the bottom. Now 1 kilogram goes to the top and becomes the numerator. Now I can cancel grams, and then kilograms is left, right? So at the end, finish the algebra with these 3 numbers, you get 0.003 kilograms, right? So this is the unit converted. So even for units with prefixes, you can still use the same technique to convert units, right? Okay. So that's about unit conversion. Now, as I said, that other quantities and units in physics, they always obtain from the 3 quantities we just discussed: mass, length, mass, length, and time. Okay, and then the units we're gonna see, okay, in this class, is always gonna be a combination of the 3 fundamental units. Okay, kilograms, meters, and seconds. Okay, so very common example, okay, in real life is the speed, right? Speed is a derived quantity. What is the definition of speed, right? Everyone knows that speed, distance over time, okay? And distance is the length, right? So you're doing length divided by time. It is a derived unit. It's a combination of these 2 fundamental units, length and time, right? And then, of course, the SI unit for speed is going to be meters per second, meters divided by second, right? So of course you may have different units for speed, like feet per second, miles per hour, kilometers per hour, things like that, okay? So let's take a look at some derived units and see how we can convert derived units, okay? So the first unit we want to take a look is the unit for area, okay? So take a look at the slide 14. We know that area is just a length squared, right? So I believe everyone knows how to calculate the area of a rectangle. It's always a length times width, right? And then the area of a circle is going to be pi times the radius squared. In each case, right, you're just doing a length times another length, right? The width we call, it's also a length, right? And the radius is a length. You do radius times radius, it's still a length times another length. But in this case, it's the same length. And pi doesn't have any unit. Pi is a pure number, right? So the SI units for area, it's going to be square meters, right? Okay? So if you see like square centimeters or square feet, right? In a problem, you definitely need to convert them to square meters, okay, in SI units, so you can use that to calculate something else, right? So that brings us to the next question I want you to practice. If I want you to convert 8 square feet to square meter, and I tell you 1 feet equals 0.3048 meters, right? I will give you all these conversion factors, but you need to know how to convert them, okay? How do you convert units? So if I know the conversion between the feet and meters, okay, is this: 1 feet equals 0.3048 meters. And I want to convert 8 square feet to square meters, okay? So now you should be careful. A lot of people, they will make this mistake. I've noticed a lot of people, they make this mistake. They will just do like this times this number, okay? But it should be careful. Now, this is a square feet is feet squared, like 2 powers of feet, right? So if you write it out, you just get feet times feet. You're actually converting 2 of these units to 2 meters multiplied together, right? So you should have two fractions to help you do that, right? You can't just have one if you know the conversion between feet and meter, right? Okay? So you're going to write two fractions, right? And put these two numbers and units in the right places to cancel these feet, okay? And then get meters at the end. So let's see, which one goes to the top, which one goes to the bottom. If I want to cancel feet, I would put 1 feet at the bottom, right, as the denominator. And then 0.3048 meters is the numerator. So this fraction is going to help us cancel one of these feet, right? And then of course, the other one is going to be the same because I'm doing the same thing, right? I have 2 feet multiplied together. I want to cancel both of them. So I would have 1 feet as the denominator, and then this 0.3048 meters as the numerator. Now, this feet is going to cancel this feet. So now you see that at the end, I will get meter times meter, which is going to be meter squared. So that's the answer, that's the unit I want at the end. Now I can go ahead, do algebra with all these numbers, right? It's going to be a times this and this divided by 1 times 1, okay? So at the end, what is your answer, okay? The answer I got is 0.7432 square meter, okay? So that's the conversion between square feet and square meters. And of course, you can, if you study volumes, okay? Volume is, we know, it's the length cubed, okay? And for a box, if you want to calculate the volume, we know it's going to be length times width times height, which is pretty much 3 lengths multiplied together, right? And then what about the volume of a sphere, okay? And then that's going to be 4/3 pi r cubed. So for the volume of anything, okay, it's always going to be 3 lengths multiplied together, right? So the unit, the SI unit is going to be cubic meters, okay? So again, if you see things in like cubic centimeters, cubic feet in a problem, you want to use this volume to calculate something else, you're going to convert everything to cubic meter, right? So let's take a look at the last slide. So now I want you to practice this, okay? Convert 5 cubic meters to 5 cubic centimeters to cubic meters, okay? If I know the conversion between meters and centimeters, it's 1 meter equals 100 centimeters, okay? So how do we convert, right? So again, cubic centimeters, it's going to be 3 centimeters multiplied together, right? That's what this cubic centimeter means. So if I want to convert this whole unit to cubic meters, I actually need to convert 3 centimeters to 3 meters multiplied together. So of course, I will need how many fractions? 3, right? I will need 3 of them. And then again, still the same fractions in this case. All right, so you write these 3 fractions. Which one goes to the top, which one goes to the bottom? I need to cancel centimeters. I will put centimeters down here and 1 meter as the numerator. So this guy is going to cancel 1 of these centimeters for me. Right? And then you do the same thing for the other 2. Exactly the same fraction. And then you're going to cancel all these centimeters. You will get meters times meters times meter at the end, which is the cubic meters. That's what we want at the end. Right? Now you can go ahead and use all these numbers to finish the algebra. Right? And then at the end, what is your answer? The answer I got is 5 times 10 to the negative 6, okay, cubic meters. All right, so this is a unit conversion. Okay. Now we're going to move on to the second PowerPoint. Okay. So we're gonna discuss one-dimensional motion, okay? One-dimensional motion, but before that, we're gonna review some of the concepts we need to use in this part, and which are very familiar to everyone, I believe, okay? So position, okay? Well, we are familiar with this concept, right? It's the location of an object, okay? So if you want to specify the position of an object in physics, what we usually do is this. We're going to pick a reference point, which we call origin, okay? And then we use some sort of scale that is understood by everyone, say SI unit, so I can specify the position of an object for you, right? So usually what we do in physics is that we draw a coordinate system, okay, and specify the x, y, z coordinates of this object. So I can specify the location of an object very precisely, right? Very precisely. So say if we just do things in 2 dimensions, okay, that's what we're going to do in this class. We're not going to go to 3 dimensions in this intro-level physics class. So this is going to be the origin I pick, right? And then in order to specify there's an object here, how do I specify the position of this object? I would find the x-coordinate of this object and the y-coordinate of this object. Say, for example, this is 4, this is 3, like centimeters, right? So I would just tell you it's at 4 centimeters and 3 centimeters. Okay, the x-coordinate is 4 centimeters, y-coordinate is 3 centimeters. So you know where this object is, right? Very precisely. Now, and then we don't really see things stay at the same location, right, around us. Actually, it's very hard to find things like stay at the same location, right? So most of the things we see every day, they are moving. They're in motion, okay? So motion is just a continuous change in the position of an object, right? We do see things moving all around us, okay? So take a look at this image on slide 2. So that's the motion of Michael Jordan, okay, dunks basketball, okay. Michael Jordan, it's always the greatest of all time, always, no question, okay. Now, as we mentioned earlier, so a very common derived quantity or unit is the speed, right? So everyone knows that the speed is defined as distance over time, right? Distance over time. Why do we use this concept? Well, because it's useful, right? We're going to see a lot of definitions in this class, okay? Why do we define these things? Why do we have so many definitions? Because they're useful, right? If you want to study things in nature, you have to define things so you can make predictions, you can explain experiments, you can even set up experiments to test your theory, okay? So some of the definitions are going to be very familiar to us, okay, which is good, okay? And some of the definitions may be not that familiar to you because normally people don't use them in their life, okay? Right? So this thing, I don't think I need to spend any time explaining what speed is, right? Everyone's familiar with this concept. So, and the definition of speed is distance over time, and usually we use this symbol v, okay, which is the first letter of velocity, to represent speed and velocity. We're going to discuss velocity in a little bit. So if something is moving in a horizontal direction or x direction, we usually call horizontal direction x direction, right? But, and then if you call that as your x direction, the definition of the speed, so if you want to put it in a mathematical equation, it's going to be this, right? So the change of the x coordinates of this object in x direction divided by the change in time between these two positions, okay? So then the unit is going to be meters per second, okay? So we're going to see a lot of equations, a lot of symbols in physics. Why do we do that? Well, because they are easy, okay, to write, to read, okay, to use, right? Because this just means speed equals distance over time, right? But if everyone agrees that v is the velocity, this is the distance in x direction, this is the time, right? So all I need to do is just write these three symbols. I don't need to write so many words, right? Like on this slide. Average speed equals distance traveled over time spent traveling, okay? So this is easy to write, easy to read, and then easy to work with, especially if we want to make predictions. Okay, we want to use the theory to make predictions. All right, so don't be afraid of equations in physics. So that's for any certain distance, right? If you do distance over time, you actually only get the average speed unless this thing is moving at a constant velocity. Usually not, right? Constant speed actually, again, it's very rare in real life to maintain something at a constant speed, right? So, but you can also take the limit when the time goes to almost zero, right? So you want to find the instantaneous speed of an object at a specific time, okay? So this definition is going to become a derivative. That's how we deal with things infinitely small, right? That's what you learn in calculus, okay? So it's just dx, I'm sorry. It's the derivative of this x with respect to t. So a very obvious example is the instantaneous speed of the car when you're driving, right? You take a look at a speedometer, it tells you the speed at a specific instant of time, okay? And then when we drive, usually the speed changes, right? But you can always read off the instantaneous speed from the speedometer, okay? All right? So, and then because speed is widely used when we study the motion of any object, so there might be different units you need to convert, okay? So if you see miles per hour, for example, all the speed limits in this country are in miles per hour, right? And then if you want to convert that to meters per second, okay? So basically, if you want to use the speed to plug it into some equations like this one and make predictions, calculate something else, you need to make sure you convert that to meters per second, okay? So that's what I want you to practice now, okay? So still unit conversion, but we are converting two different units to other two units, okay? So say if I want to convert 65 miles per hour to meters per second, okay? So first of all, I need to know the conversion between these units, right? Miles and meters, it's going to be the same we saw earlier, and the hours and seconds, we also saw that. Okay, so if I want to convert miles per hour to meters per second, miles per hour is just miles divided by hours, right? So you have two units to convert. You need to convert miles to meters, and also hours to seconds, right? If you only know these two conversions, how do we do that? Well, let's write this guy as miles over hours, right? So now you see that I want to convert miles to meters and hours to seconds. I still need two fractions to help me do that, right? And then now you're going to put, these two fractions are going to be different, right? Because I'm converting two different units, okay? You're going to put these two numbers in the right places and these two numbers in the right places in this fraction, right? So for example, if I want to convert miles first using this fraction, what do? I would put 1 mile down here, right? Then 1609.34 meters becomes numerator. Now hours and seconds, I want to cancel hours, right? So I would have to put 1 hour at the top, so it's going to cancel these hours here. Then I will have 3600 seconds down here, right? So now let's first work with this unit. this cancels this, right? And this cancels this. So at the end, what are the units I get? At the top, I only get meters left. At the bottom, I only get seconds left, okay? So that is the SI unit I want at the end. So then I can just go ahead and do algebra with these numbers, right? And then if you do the algebra, what is the answer you got? The answer I got is 29.1 meters per second, right? Okay, so that's how we convert miles per hour to meters per second, if we know the conversions between miles and meters, hours and seconds, right? So we know that when you drive, okay, say if you're driving, right, both the speed, the magnitude of the speed and the direction are important, right? You definitely need to know the direction you're driving if you have a destination. For example, if you want to drive to Charlotte, okay, you have to go south. You don't go north. If you go north, well, eventually you may get to Charlotte because Earth is round, okay? But you don't want to do that, right? So you still want to drive to the south so that it can get to Charlotte. So there are some quantities in real life, okay, they must also have direction. When I specify them, when I use them, I need to specify the direction, okay. Some of the numbers I use in real life, I don't need to specify a direction. They don't have direction. So we have two fancy names for them. We call them scalars and vectors, okay, if you have heard them before. So scalar only has a magnitude, okay? So if you use a scalar, it only has a number and a unit, of course a unit, right? For example, temperature. Temperature is a scalar, right? If I tell you the temperature of today's temperature, I'm not going to tell you it's in this or that direction, right? I'm just going to tell you the temperature, the number, and the unit, right? Fahrenheit or Celsius, right? Okay? Vector, like the speed we're talking about, or velocity, okay? Or the force, as we're gonna discuss later, okay? They will, if I want to specify this thing, I will give you the number and also the direction, right? Because velocity in this direction, that direction, they're totally different. The effect of driving in this direction, that direction, you're gonna end up in two different places, okay? So they're called vectors. They have a magnitude and a direction. So when we draw a vector on a piece of paper, what we usually do is we draw an arrow, right? And then we use the length to represent the magnitude quantitatively, okay? And then we use the tip of the arrow to present a direction, okay? So that's how we draw a vector, okay? So that brings us to these two different concepts, distance and displacement, okay? So distance is a scalar. It's the total length of the path an object travels. And displacement is another concept. It's a little bit similar to distance. Sometimes it's the number of the magnitude of displacement is going to be equal to distance, but it's a new concept. It's a different concept defined in physics. It's the straight line distance between the initial and final position with the direction. So displacement has a direction, okay? It's a vector we define, okay? Why do we define that? Because it's useful. Sometimes we need to use the straight line distance between the initial final positions and the direction, okay? To make some predictions, to do calculations, okay? That's why we define it, okay? And we're gonna see an example where this displacement is useful. It's a very useful concept, okay? So that's the difference between distance and displacement. So again, a very good example is this on this slide. Take a look at the trip made by this car, okay? If the car drives to the east for 4 miles, right, and then north for 3 miles. Okay, so this helps us to understand the difference between these two concepts. The distance, okay, it travels, you can say it's going to be 7 miles, right? You add these two guys together, you get the 7 miles. What is the displacement? From the definition, everything has a definition in physics, okay? We're going to draw, if I say what is the displacement of the car in this trip, it's going to be an arrow you draw from the initial point to the final point. Okay, so that's the displacement. And the displacement has an angle in this direction. And then if you want to describe it in words, you can say upright. And then the displacement, the length of the displacement, 5 miles, right? If you use the Pythagorean theorem, you can find that. Okay, so that's the difference between displacement and distance. As I said, the reason we define displacement is because it's useful. Because velocity in physics is defined as displacement divided by time, not distance divided by time. And because displacement is a vector, so the velocity you define using the displacement is going to be a vector. Okay, so usually I would use an R with a arrow on top of it. So that's how we write the symbol for a vector. We write the symbol and then we put an arrow over the symbol to represent a vector. That's what you usually do, right? That's pretty much like everyone does to write a vector, the symbol of a vector. Okay, so the SI unit is still going to be meters per second, right? And then the difference between velocity, we call this guy velocity, okay? We call the speed, as we define as distance over time, as speed, okay? But people use these two words interchangeably in real life. And we're going to also do that in this class, unless I want to specify them, right? But if I want you to find the direction and magnitude of the velocity, I will specify it in a question, okay? So you don't need to be worried about these two names. We're still going to use these two names interchangeably, okay? So another thing we usually define is this. Once we define the velocity as the changing the displacement over time, okay? Why do we define that, right? That again, that tells you how fast this object is moving and also the direction. And then sometimes we are interested in the changing velocity. We are interested in how fast the velocity is changing. As I said, it's actually very hard to maintain a constant velocity in real life, right? Look around you, right? Things are moving. Right? It's very hard to find anything moving at a constant velocity for a long period of time, right? So the velocity always changes. So if you want to study motion of objects in real life, right, sometimes you are interested in how the velocity changes. So that's when we define acceleration. So the acceleration is defined as the changing velocity divided by changing time. Okay, so it tells you how fast the velocity is changing, okay? So of course this unit is going to be meters per second divided by second, so that's going to be meters per second squared. So that's a different unit. And then the instantaneous acceleration is defined as the derivative of this velocity over time, okay? So these are the quantities we're going to use to study the motion of an object, okay? And then next time, because they are all vectors, so next time we're going to discuss how to work with vectors, because vectors are very important in physics in this part, and a lot of people, they have difficulties working with vectors. So that's what we're going to do next, okay?